I'm Dr. T and welcome to my office. Today I'd like to talk a bit about astronomy in a two-part video series looking at the Earth and the Sun. But first I'd like to introduce the idea of astronomy and then jump into more about the Earth and the Sun. Specifically in the first video, looking at the Earth and the Sun on 2 days of the year, the equinoxes. When we think of astronomy, obviously we're thinking of, big telescopes and maybe space travel, etc. But if we go back in time, astronomy is a somewhat different kettle of fish. It's looking at the sky, trying to understand what's going on, but quite often we're looking to the sky not just to ask the question, what is there? Why am I seeing what I'm seeing? Questions that we ask more today. But in the past, we would quite often look to the sky and go, what time is it? Where am I? Or fields that we would now call chronology and cartography. And astronomy has been uniquely placed to help these fields and to really be the backbone of a lot of our society. Because a lot of what we do is governed by our relationship with the sun, as well as other things that are not on this planet. So astronomy is going to be looking at those individuals, well, not individuals, those things, I should say, and trying to understand what's going on there, and in turn understand what's going on with our daily lives. So to start with, I'd like to look at, kind of a little closer to home, the Earth and the Sun. And for this video, I'd like to look at these by thinking about the way the Earth and the Sun are related to each other on 2 days of the year. So we're going to ignore 363 days of the year, and we're going to look at 2 days. And these are the equinoxes. And in the next video, we'll look at the rest of the year, but things are a little bit simpler when we think of the equinox. Okay, so you've got the Earth. The Earth is an oblique spheroid. That means it's kind of like a sphere, but it's a little shorter on the top and bottom, and it's a little wider around the middle. Because the Earth spins, the centrifugal force kind of nudges out the middle, and thus the Earth is not a perfect sphere. It's definitely ball-shaped, and if you looked at it, good luck telling it's not a sphere, but it's not a perfect sphere, and there are some interesting consequences to this. Things like the force of gravity or the height of the atmosphere, depending on where you're at. Although that's a little bit beyond the scope of this video. Now, because the Earth is a spinning sphere, we get some rather interesting effects. The majority of the light we get here on Earth comes from the sun. Now, at times, that light might be bounced off of the moon or off of other planets. But when we are able to see the sun directly, it produces a lot of light, and that gives us enough light to do most of what we need to do. So as we stand on the Earth, we are moving, but kind of like a scenario where you're passing a slower going car on the interstate or passing a few trees or fire hydrants. The trees and fire hydrants aren't moving. The slower moving car is moving, but not as much as you. So it looks like everything else is moving, and that's because it's relative to you. So we are on the Earth is spinning, so it looks like everything out in space is moving, and it looks like it's moving in a big circle around us. Of course, from one point of view, you could say that it is. Obviously, we're the one moving, but hey, it's actually useful to think about the still things moving and having a point of reference that moves. So assuming your point of reference is moving, aka you're thinking about yourself and what you're seeing, it appears that the sun is coming up in the east, traveling across the sky, and it travels in a bit of an arc throughout the course of the day, and then eventually sets in the west. Now obviously, once again, the sun isn't moving, you are, so it's your point of reference that's changing. But you get the same result either way. So we'll think about ourselves. Now, as the sun moves across the sky, of course, you get light. Once it sinks below the horizon, you're now facing away from the sun. A couple of things happen. One, you're now able to see other stars which are much, much further away. Many of them are just as bright or much brighter than the sun, but they are much, 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 much further away. And so they are much dimmer. So now you can see them because you don't have the giant brightness of the sun blotting them out. Of course, if you live in a place with light pollution, well, the sun's not blocking it, but everyone's lights are. Okay, now those will appear to travel across the sky, rising in the east, setting in the west. Now, some of them, depending on where they're at, may appear to make little circles in the sky, kind of thing. They never sink below the horizon. Those would be closer to the pole. So if you're in the northern hemisphere, the stars that are more closely lined up with one of the poles, so imagine a line going from the center of the Earth to that star. You know, if that line happens to intersect the Earth near a pole, or the surface of the Earth near a pole, then of course this would be a more polar-based star. The most famous of which is Polaris, the North Star, which almost, but not quite, perfectly lines up with our North Pole. Once again, it's a little bit off, but for most tasks, it's pretty good. Okay, and so the stars will cross the sky. As you rotate back, then all of a sudden, our nearest star, the sun, will start crossing the sky, and it will become light. For ancient civilizations, and frankly for you and me today, this is a big deal. When the sun is in our field of view, we're going to get lots of light. It's going to warm up. And as it's warming up and getting brighter, we can go out and we can do things. Or if you happen to live like I did in Yuma, Arizona for a while, you go inside where there's air conditioning if it's the summer because it gets hot down there, and you come out at night. Hey, actually works beautifully. Okay, so this is, of course, a nice thing to think about. And one important piece of information you want to have is, well, how much light do I have left? Do I have time to go to town and come back without it getting dark? You know, once it's dark, nah, it's hard to see, especially before you have artificial lighting. Also, you know, how long have I been doing this thing? How much money should I charge the guy that said he would pay me to do this for half a day? Has it been half a day? Can I quit? This is kind of annoying, you know, kind of moving on. So one of the earliest timekeeping approaches is the use of a shadow. So if you take a stick or a thing and because you don't really want to look at where the sun is directly because it's bright, it'll hurt you. So you look at the shadow and it's going to make an arc that's opposite of where the sun is. So yay, you can take the arc, measure that, and knowing where the sun is relative to that arc, things go well. This is the beginning of the sundial. You can make a few optimizations to the sundial, make it work a little bit better throughout the year. And yeah, so things are working well. Originally, the idea of an hour was not 60 minutes. Each one of those was 60 seconds. Each second was defined by a certain number of vibrations of a cesium atom. Instead, it was defined simply as a 12th of the day. In the winter, you would have shorter days, and thus for shorter hours. In the summer, you would have longer days and longer hours. But we're focusing a bit more on the equinox. So, hey, half your time is in light, half your time is in at night, at least twice a year. Hence the equal of the equinox. Now, a couple other things you're going to notice. If you're sitting on the equator, on the equinox, if you imagine the center of the Earth, you and the sun, it's all going to form a nice line. But if you start going up or down from the equator, so you move to a higher or a latitude closer to one of the two poles, then what you'll start noticing is you're no longer straight in a line. The sun isn't directly above you. Definitely not at the highest point the sun gets, because once again it kind of goes in an arc. Okay, this is interesting, and this is actually it has two major effects for you. One, as you're looking at the sun, because you're looking at an angle, it's lower in the sky, the light from the sun is going to be coming out fairly parallel. So if the light is coming out and it's coming parallel and it hits the ground nice and square on the ground, then it's kind of like taking a flashlight and pointing it straight at a wall. All the light is concentrated on a rather small, bright spot. Now, obviously, there's enough light that it's hitting everything, but if we think about just, a few rays coming down. Now, as you get up into higher latitudes, then you start seeing the light and it's hitting the ground, but the sun isn't directly above. It's not hitting square on the ground. Instead, it's coming in at an angle. So again, if you take a flashlight, point it at a wall, and turn it, then this spot on the wall is going to become wider but dimmer. The same amount of light, but it's spread over a bigger area. Now, of course, the amount of brightness is going to be possibly noticeable. It still gets bright pretty up north, or pretty far up north. But what you do find is that, hey, it's colder. You get less light per square mile, and thus less heat gets to bombard the surface, and thus the hottest of the hot day, you don't have as much light coming in, and so given the same soil, etc., because of course that stuff matters, it's not going to get as warm once you're farther north, and that's what we see. Climates towards the equator, very toasty. Climates towards the poles, very chilly. They don't get nearly as much light from the sun. This also brings in another feature for us, and the beginnings of our idea of cartography. Obviously, if you're living in a relatively small area, you're not traveling that far, you can use landmarks to figure out where on Earth you are. However, if you're, say, on a boat out in the ocean where there's no land, so you can't have a landmark, you're going to have some problems. Now, there are ways around this, things like compasses, but those were actually fairly later inventions, and the Polynesians did some really interesting things with ocean currents. But another approach you can take is to look at the angle of the sun at its highest point, so high noon, insert Western music here. Look at the sun at its highest point relative to the horizon. That tells you what kind of latitude you're at. So a lot of early sailors, starting with kind of the Islamic area around the Indian Ocean, but also continuing on later to European sailors, would hug the coastline going north or south, look at the longitude, sorry, the latitude, my bad. Longitude, we'll get to that later. That one's much harder to do. Okay, we'll use the latitude by looking at the angle between the sun and the horizon, or alternatively, a star at night, such as Polaris, the North Star. Once you knew what latitude you were at, you could then just cut as best you could straight east or west, and if you had a compass, that would be really helpful here. Goes hopefully straight east or west, and then you would land where you wanted to be at. Yay. Now, if you look at the Earth, you can imagine a grid. Latitudes are lines that run circles going around the planet, and they're equally spaced, and they're going north and south. Or they go east and west. They stack up going north and south. They tell you how far north or how far south you are. Now, if you want to slice the Earth in pi wedges going through the poles, those would be lines of longitude. And they tell you how far east and west you are. That's actually basically the same idea, but it needs one more piece of information. Obviously, you're east or west from a point relative to someplace. The way you can tell this is by looking at when your high noon is, so when the sun is at its highest point, and thus you are pointing as close to straight at the sun as possible, relative to when your point of reference is. Today we typically use Greenwich, England, although in the past everyone had their own preferred point of reference. The French obviously used Paris, not England. Now, that's fairly straightforward. I know what time it is. I know where I'm at now. I know what time it is in Greenwich, England, and therefore I know how far the Earth is rotated, relative to those distance. I've moved that distance, so yay. Only small problem. How do I know what time it is in England? I'm not in England right now. And that's one of the major difficulties for longitude, is trying to get a good timekeeping device that's accurate enough. This isn't solved until, I want to say the 18th century. I'll put a bubble when that actually gets solved. So this is a fairly difficult thing to do. Occasionally you can do things with like eclipses or something where you can figure that out, but most of the time Yeah. By the way, you don't have to do this based on the sun. You can do this based off of a star or whatnot. Okay, so next time, let's talk a little bit about seasons. And I will see you next time.